information content, entropy, information gain. If you remember in the discussion on decision trees, we had been using the notion of entropy and information gain, but we wrote down a bunch of formulas without actually having derived them. In today's lecture, what we're going to do is to derive those formulas from the ground up. We'll be starting off with the basics of information theory, and this will be a shortish kind of a discussion video today. So let's start with the discussion on information content or self-information, which is generally represented by the character I. So it's a basic quantity which is derived from the probability of a particular event occurring from a random variable. It needs to follow three axioms. So think about when you're encoding the information or the surprise associated with any event. What are the axioms that you would want to be obeyed? So firstly, if an event is 100% probable, then there is no information to be gained because you already know that that event will happen with certainty. So that's the first axiom. With this axiom in mind, could you think of the next axiom? The next axiom is that the lesser the probability of an event to occur, more is the information if that event occurs. So more information is yielded by that occurrence of that event. And the third one is if two independent events are measured separately, then the total information is the sum of the self-information of these individual events. So we'll be looking at all three of these axioms with the help of some examples, and I'll be giving you a formula for self-information. So while I'll be giving you the formula directly, if you go through the Wikipedia page of information content, using these three axioms, you should be able to derive that formula also. So the formula for information content or self-information I of x, sometimes written I sub x, is minus logarithmic base b of the probability of x. So here what is happening is an event x with the probability p is occurring. So you could also write this in shorthand as minus log base b of p. Now in the previous discussions we generally used b equal to 2, which is base 2. So in such cases the units of information is Shannon or bit, where Claude Shannon is the scientist behind information theory. If you use b equal to e, so in that case the units of information are NAT, which is for natural. So NAT stands for natural because you're using the natural base for the logarithmic here. So what we'll now try to do is to show that this definition of information content follows these three axioms. I would suggest you to pause the video for a second and try to see if these three axioms are correctly will be correctly shown by this formula. So the first axiom, let's take an event with 100% probability. So thus we can rewrite the formula for the specific case as I of x is equal to minus log base 2 and the probability of x is 1. This quantity is 0. So this confirms the first axiom that an event with 100% probability will yield no information. So this is also common sense. Like let's say if you know the certain outcome, then there is nothing new you can expect to learn from that. Can you try to validate or verify the second axiom using this formula now? Okay, so the second axiom is that the lesser the probability of an event, more is the information it will yield, right? So if the probability of an event is 0, let's say, so it is extremely unlikely or close to 0, then the information would be tending towards information content of that event would be tending towards infinity. What this means is that for example, if there is an event like, you won a lottery, so the probability of that event is extremely rare, and the information that that particular event, occurrence of that event will yield is huge. On the other hand, if you go back and take the other example, that so the event is that you did not win the lottery. That is almost 100% probable. So losing the lottery or not winning the probability, knowing that event does not yield any new information for you, right? Let's now try to look at the third axiom. Okay. So for this, the statement was two independent events are measured separately. So first, let's take two independent random variables, capital X and capital Y, whose probability mass functions are given by P of capital X and function of small x and P of capital Y function of small y. So if we were to write the joint probability mass function, so in this case it would be decomposed as the product of the individual PMFs, because we've mentioned that these are two independent events, right? So if these two events are independent, then if you were to write the information content over the joint, so it would be minus log base to the joint PMF, right? Which we can decompose using the decomposition of which occurs due to these two random variables being independent. So I just replace this line minus log base to this particular line with this line, and I'll end up with minus log base to pxx and minus log base to pyy, which is the same as the information content of x and the information content of y. So is verifying the which is verifying what we had written as the third axiom. So this is occurring because logarithmic breaks down the product of, so the product of log of 2 can be written as the sum of the logs of individuals. So that's the reason why this particular axiom holds. And this is where the logarithmic comes into the picture. As mentioned, you could look at the Wikipedia article and you could start off with these three axioms and then conclude that logarithmic is the function that you'd want to use. The third axiom definitely gives you that strong hint because you want this decomposition to hold. So you'll want something of where the product is broken down into sums of individuals. So let's take a few simple examples to understand this concept better. If we have a fair coin and we toss it, so fair coin means that the probability of a head and the probability of a tail is 0.5. So the information content of the event that a head occurs is just the negative of the logarithmic base 2. I've just chosen log base 2 here. So this is going to be measured in terms of Shannon of the probability of the occurrence of the event. So this is minus log base 2 half, and half can just be written as 2 raised to power minus 1. So this is 1 channel. Similarly, the self-information of the event that a tail has occurred would also be 1 channel. Let's take some other example. Let's take an example of a biased coin where the probability of a heads is now 0.9 and the probability of tail is 0.1. So without doing all of the maths, can you also confirm the intuition or your understanding that the information content of the event of tail occurring would be much, much higher because the event is very less, has a very less probability of occurrence compared to the head occurrence. And if a head occurs, you will not have as such any new information because that's very likely to anyway occur. So we calculate the information content of the event that a head occurs for this biased coin. So this is minus log base 2 of 0.9, which is 0.15, a small number. And the information content that a tail occurs is 3.32, much, much larger than the information content of a head occurrence. Let's now take an example to understand the third axiom better. So we'll take a case of two paired dice. Both x and y are two discrete uniform random variables, whose values can be from 1 to 6, and they have an equal probability of each of these symbols 1 through 6 to be chosen. So the question for you is, what is the information content of x equal to 4 and y equal to 2? So both the dice are going to be now independent of each other. Can you think and come up with the answer for the information content of this joint event to occur? Okay, so this can be written in two ways. First, we use the formula where we are breaking down. So we go back to the third axiom. We break down the information content of two independent events as the sum of the information of these self-information of these individual events. So thus we break this down into the information of x equal to 4 for the first dice and y equal to 2 for the second dice. Now the probability of x equal to 4 for the first dice is 1 by 6. The probability of y equal to 2 for the second dice is 1 by 6. Thus this whole calculations comes out to be minus log base to 1 by 6 minus log base to 1 by 6, which is 5.169 channels. But instead of breaking this down into two individual self informations, we could have also thought, so if you write the joint PMF of x and y, then what is the probability of occurrence of x equal to 4 and y equal to 2? So it would be 1 by 36, right? Because for each value of x, you will have 6 values of y and you have 6 values of x, and each of them is equally likely to occur in the joint PMF. Thus, the joint PMF, the information content for x equal to 4, y equal to 2 can be written as minus log base 2, the probability of x equal to 4 and y equal to 2, which is 1 over 36, which is the same quantity. And you could also do the same for any arbitrary categorical distribution where you can define different amount of probability. So you just need to define the probability mass function, and you can just use the same formula that we've been using thus far. Let's now look at the link between entropy and information content. So entropy, like information content, is a very basic quantity information theory, and its interpretation is that it is the average level of information or surprise that occurs. Now, where do we, or what do we do this averaging on, right? So that's the question. Let's go back to the example. So in this case, for the fair coin toss example, the information content for, we have information content for head, we have information content for tails, right? Could we compute an average information content over all the possible values that the coin could have taken? Yes. So that's exactly what entropy means. So it's for the fair toss coin, probability of head is probability of tail is 0.5. The information content of tail equal to information content of head is 1 channel. And we define the entropy using the symbol h. So h of x is now the probability of, so it's, since it's defined in terms of expectation of the information content, so you just write down the formula for expectation of any random variable, so which is the probability of x times the function that you're trying to find the expectation over. So in this case, entropy is given by h of x equal to probability of heads into the information content of head plus the probability of tail into the information content of tail, which is 0.5 into 1 plus 0.5 into 1, which is 1. Right. So this is where the formula for entropy comes from. So when we generally write in terms of minus p log p, minus pi log pi, where pi is the different values that can be taken, the probabilities of different values that can be taken. So that's how we generally write. We open up the formula for expectation. We sum over i's, and this is the PMF of xi multiplied by the occurrence of event the information content of the event xi, which can simply in shorthand be written as minus pxi log pxi, the summation over all the possible values that could have been taken, right? So we can, given this simple data set where we have many attributes, but we're for now considering only the input attribute temperature and the output attribute of concern play. And you have only 4 examples. In 2 examples you play, in 2 examples you don't play, right? So using this formula or the formula that we've been seeing thus far in the discussion of decision trees, could you write down the entropy for the random variable play? So in this case, we're going to just treat it as a random variable. So we can just write that as the minus p probability of no times log base 2 probability of no minus probability of yes log base 2 probability of yes, which is minus half log base 2 half minus half log base 2 half, which is 1, right? Okay, so far so good. Now let's introduce another concept called conditional entropy. So this is similar in definition to conditional probability. We're going to be saying that the conditional entropy of y given x, written in the symbolic form as h of capital Y given capital X, is minus summation over x belonging to the support of x, y belonging to the support of y, probability of joint probability of x and y, and multiplied by logarithmic of joint probability of x and y divided by probability of x. Now this looks like a very weird looking formula, and it looks a fairly complicated formula. Let's try and understand this derivation behind this formula, and we'll take some examples to better understand what conditional entropy even means. And finally, we'll be able to build the link to information gain. So we said that we want to find out h of capital Y given capital X. First, let's try to find out the conditional entropy of capital Y, given that x has taken a certain value, small x. So the entropy of capital Y conditioned on capital X equal to x, right? So this can be written by the formula summation of y belonging to support of y, probability of y equal to y given capital X equal to small x, and logarithmic of capital Y equal to y, capital X equal to x. Could you think of where this formula came from? So this is basically the same formula that we've been seeing used in the sense of conditioning now. This is the same minus p log p formula, and you're summing it over all the values of y in this case. Right. So to look at it in a more detailed sense, you have the information content, which is logarithmic of the probability of capital Y equal to y given x equal to small x, and the minus sign here also, and then you're doing an expectation over that. So you look at the expectation over that, which is to see all the possible values of capital Y equal to small y, right? So that's how we've previously also done. We wrote down the formula of entropy of x equal to the expectation of the information of I of x. So you'll replace x here with y given x equal to x, and that's how you'll be able to find out this, write down this conditional entropy of capital Y given capital X equal to x. Thus, the entropy of capital Y given capital X is the expectation of this quantity the above mentioned quantity over all possible x, right? So, see, whenever you calculate the expectation over all possible x, you do a summation or integration in the case of continuous variable, a summation over the entire support of x over the probability of x times the function you're trying to find the expectation over. So the function we're trying to find the expectation over is the entropy of capital Y given capital X equal to x, right? So all we now need to do is to expand this out, and so we've written the entropy of Y given x as summation over the support of x, probability of x times the conditional probability of y given x equal to x. So capital X has taken a certain value x, which we can, from the above equation, for the entropy of y given capital X equal to x, we just substitute that over here. So you have this formula now, and now so there is a minus sign which comes over here from here, and then all you need to do is to do some manipulation. So you write probability of x into probability of y given x if you just use Bayes rule. So this is just the joint of x and y times the logarithmic of y given x. Y given x could again be written as the joint of x and y divided by the probability of y using Bayes rules. So thus we can write the entropy of y given x as minus times summation over the support of x, summation over the support of y, joint probability of x and y, and multiplied by logarithmic of joint of pxy and divided by px, right? But when we were discussing the case for decision trees, we looked at a somewhat simpler formula when we were talking about things like information gain. Could we recover those formula? Let's see. Let's try to write this formula in a more simpler sense. So we have, and this rule is also called the chain rule of conditional entropy. We have the entropy of y given x as summation over x, summation over y, and minus sign outside, times pxy logarithmic of pxy divided by p of x. All I'm going to do is to break down this term of logarithmic of pxy divided by px as the numerator minus the logarithmic of the numerator minus the logarithmic of the denominator. So this gives us minus summation over x, summation over y, pxy log pxy. Now, what is this quantity? This is just the entropy of the joint of x and y as per the formula of that we've been seeing for entropy. And the second term that we have is plus summation x over x, summation over y, pxy logarithmic of px. Now let's just consider the summation of pxy over y. Now this is just marginalization. You're trying to sum out over all possible values of y, which will give us px. So finally we are left with hxy plus summation over x, px log px, which is nothing but minus the entropy of capital X. So thus we can write the entropy of y given x is the entropy of joint of x and y minus the entropy of x, right? And let's try to look at this some example to understand this better. And if this looks somewhat similar to the Bayes rule, then it should make sense. Just fairly similar to Bayes rule in terms of regular conditional probabilities. Only the difference, so minus and divided by are going to be interchanged here. Let's get back to the example of playing tennis based on temperature and other attributes of concern. So the question I'll have for you is can you calculate the entropy of the play variable knowing the temperature variable, right? So this is fairly similar to the question we face in decision trees. What is the information gain that you get once you observe a certain variable, or once you've stepped down one level in the tree if you choose an attribute. So we have thus far seen that this is the formula for the entropy of y given x. It is the summation over the support of x, of probability of x given the probability of x multiplied by the entropy of y given x, capital X equal to small x, right? So all I'm going to replace here is now do the replacement of y, capital Y with play, and capital X with temperature. And capital X equal to x means the different values that temperature takes. So capital X, so temperature equal to hot, temperature equal to cold, and temperature equal to normal, right? So I'm going to write down the respective entropies, the and multiplied by the probability of that particular subset. So the probability that temperature is hot, in this case that is 2 or 4 or half, multiplied by the entropy of play, given that the temperature is hot, right? So what is the entropy of play given that the temperature is hot? You are restricting yourself to the cases, these two cases, right? The entropy of play given that the temperature is hot, plus the probability of temperature equal to cold. So that's 1 over 4 times the entropy of play once you've observed that temperature is cold. Similarly, probability of temperature equal to normal, which is 1 by 4 times the entropy of play when the temperature is normal. Right? So does this already ring bells in terms of the formula for information gain? It should, because it's now derived from the same basics. And finally, using all the derivations that we have seen, we can write the information gain on play, having observed temperature, as the entropy of play minus the entropy of y given x, and y I've mentioned as play and temperature as x. Right? So this is how the formula for information gain is derived, where the entropy of y given x is written in this particular fashion. In the next lecture, we'll be discussing about the notion of entropy for continuous variables.